Hi. Um, so yeah, the thing I would like to talk about now is kind of a continuation of some of the things that Antonio has already talked about. And it's a work that I've been doing with Antonio and some of our collaborators in Boulder. And it's a work on Koopman theory for enhanced Pacific SST forecasting. And this is a part of my PhD project that we have been carrying out for the last 2.5 years, and that we started with two main ideas in mind, two main goals. The first one was to try to build a nonlinear extension of the limbs that we have been already talking about, using Koopman theory and trying to apply it for developing, hopefully, enhanced SST forecasting systems. And the second one was trying to gain some insight into the application of Koopman theory in climate science. So let's start talking two words about ENSO. So we do know, I think all of us know, that the climate system is a very complex one that is formed by the interaction of many different processes that interact among them at different timescales and also spatial scales. And among all these processes, El Niño Southern Oscillation, or ENSO, is the most important atmosphere-ocean couple mode. And we do know that it modulates climate anomalies worldwide, and therefore there is a great societal value in improving ENSO seasonal predictions. On the other hand, though, we do know that there are general deficiencies in global climate models or in the numerical models that Antonio was talking about. And the prediction skill of these models is comparable to that of vastly simpler empirical models, just as LIM, which is DMD. That's how we call it in the climate field. Antonio has already mentioned this, but LIMS have been used for almost 30 years for forecasting ENSO. They were first implemented in the 90s, where they found that there was long lead predictability. And then the limbs have been like very thoroughly studied through the last 30 years. Also, the colleague behind, whose name I don't remember right now, mentioned cyclostationary limb. They have developed some variations. For example, well, they started including more variables because they discovered that it led to longer predictability in the longer lead times if you include not only SST, but also some variables that relate to the subsurface processes, for example. They also developed the cyclostationary limb, in which they are getting estimates of the DMD operator from the different months of the year to account for seasonality. So the key point here is that they have thoroughly investigated them, they have also optimized them, and they are operationally used nowadays for doing ENSO forecasts, together with the global climate model forecasts. So they have similar skill with much lower resources. And so they are very, very good benchmark for data-driven ENSO forecasting systems. However, of course, LIMS rely on linear dynamics, and therefore they have the limitations that any linear model will give us. And that's what led us to Koopman theory, and especially to the algorithms that have been developed in the last decade for estimating in a data-driven way estimates of the Koopman operator. So the link was pretty clear. If LIMS have been used successfully during the last years to compute ENSO forecasts, and we do know that LIMS are just a specific case of the broader Koopman theory framework, we could try to use these algorithms to try to compute approximations of the Koopman operator that use nonlinear similarity measures. And yeah, that's what we have done. And this is the part of the work that Antonio showed you before. This was our starting point before my PhD started. This is a work by Antonio in 2021, in which they applied transfer operators to predict SST. He already showed this. They applied it to one-dimensional Niño 3 time series and also to two-dimensional Pacific SST. This was a preliminary study, and they found that, for some of the trajectories, well, let's see if this works. Yeah, for some of the trajectories, we found increased skill, but there was not an intensive study of the predictability, the skill gains that we found. And also we had some, we suspected that we were facing, we suspected that we were facing some robustness issues in the estimates of the Koopman operator, and we were also wondering how much data do we need to properly fit these operators, because this is a problem in many data-driven or machine learning approaches. Like when you are trying to get the nonlinearities, you need much more data than you need to fit just the linear part. So this was the motivation that made us thought that we wanted to do a work and a studying like the testing the training period sensitivity on how much data do we need to fit these operators. For doing so, what we decided is to take a very, very long time series. We took synthetic data from a model that is called CSM2, and we took the P-control data, which means that is data in which we do not have forcing. So it's stationary dynamics, and we have very long time series, so we can study this sensitivity. And what we did is to divide the data following different lengths, for example, 50, 100, 200 years, and so on. And then we compared the modes and the eigenvalues, both for the linear and nonlinear kernels, to try to get a sense of what was happening behind behind. So I told you, like, 2 words in the data. We were using the 2,000 years of data, both for SST, so sea surface temperature and sea surface height. We were using monthly mean anomalies, and we had 2,000 years of stationary dynamics. Then we took the whole Pacific area, and we did the EOF or PCA or SBD dimensionality reduction. Antonio talked about it. We focused on 2 different configurations, keeping just 30 EOFs, so the 21st SST EOFs and the 10 first SSH EOFs. And we did this because this is a very, very common setting for limb forecasting. As Antonio said, we need to do an EOF dimensionality reduction for being able to apply limb. And then we also kept all of them. And we have been using the Stefan's code, the KEDMD algorithm, comparing both the Gaussian and the linear kernel, and then we evaluated our forecast on the Niño 3.4 index, which is the temperature average over this box in here. Okay, so let's have a look on some of these spectra. Here what we have is composites of the eigenvalues for the different estimates. So we have different chunks of the data. For example, here we have 2 chunks of 1,000 years, and here we have 40 chunks of 50 years. And each one of the colors are the eigenvalues for each one of these estimates. And what we can see pretty clearly is that diminishing the length of our Koopman operator increases the variability of the eigenvalues. So we have more noise when we are trying to get the eigenvalues from very short Koopman operators. However, even when we took 1,000 years of data that we will never ever have in the climate field, they seem to be robust enough. Here we have the spectra for the 2 chunks of 1,000 years. So we have 2 different estimates of the Koopman operator, both of the same length, and they look pretty different anyway. If we do the density that Antonio was showing before, we can see that the peaks do not correspond among the 2 different estimates. This is a problem that does not happen when we are using the linear kernel, though, because they seem to be much more robust. And even with much shorter lengths of the data, we can get robust estimates. So the problem is, okay, we want to make accurate forecasts. We want to get robust estimates of the Koopman operator, but not even 1,000 years seem to be enough, and we will never ever have 1,000 years. So we came with this idea of doing Koopman ensemble forecasts, in which what we are doing is we are dividing our total data. As I mentioned before, we are getting different estimates of the Koopman operator, and each one of these estimates is used as an independent model for doing a forecast, starting from the same initial conditions. And then we can take the ensemble mean, and we can see if this ensemble mean is behaving better than the members. And this is exactly what you can see here. And I really like this figure because I think it gives an idea of what is going on. Here we have the linear forecast, and here we have the Gaussian forecasts. The gray line in the background is the observations, or the model observations that we are comparing to. And each one of the 20 red lines, because you have to trust me, there are 20 different red lines in here, is one of the ensemble members that we computed. It's a forecast made with each one of the different Koopman operators. And then we have the blue line, which is the ensemble mean, so it's the average of all the red lines. When we are using the linear kernel, what we see is that all the red lines are very close among them. There is almost no spread. It's a very robust set of forecasts. On the other hand, when we are using the Gaussian kernel, the forecasts, especially for longer lead times, they seem to be all over the place. However, when we took the ensemble mean, which is the blue line, this ensemble mean of the forecast that look like they are all over the place is performing much, much better than the very robust linear forecasts. So we can see this here. Here we have 2 different cases. We computed the Koopman operators with 400 years of data and with 50 years of data, which is very little. Even for a limb, 50 years is kind of, on the edge. So here we have the ACC, the correlation of each one of the different forecasts, and then we have the correlation of the ensemble mean. And what we see is like there is a skill boost by taking the ensemble mean. The ensemble mean in the Gaussian case is performing much better than any of the single ensembles. This does not happen when we are using the linear kernel, or it's happening in a much lower scale. When we are using very short linear Koopman operators, there is an improvement by using the ensemble mean anyway, because 50 years is not enough for getting answer, not even with a linear model. But what we can see is when we are using 400 years of data, taking an ensemble makes nothing for the linear case because they are very robust. While it still makes a difference when we are using the Gaussian kernel. So we can see this all together in here, where the dotted lines are the behavior of the ensemble members, and the solid lines are the behavior of the ensemble mean. And what we see is like when we are using the ensemble members, there is not a big difference in the performance of the linear and the Gaussian kernel. However, when we are having a look on the solid lines or in the ensemble mean, there is a big gain in the skill when we are using the Gaussian kernel. We see that it's almost 4 months in this case, actually. So what we see is the Gaussian ensemble mean is performing better than the lim ensemble, even if the individual forecasts are not. And these results that I'm showing are for the 100-year-long operators, but of course we did it for all the different lengths that we mentioned. And what we can see is like the 400, 200, and 100-year-long operators, they are performing very, very similarly. They are all together here, while the 50 and the 1,000-year ones are performing worse. So what do we get? What we know is theory is the best it is performing. Yeah, of course, we did this for 2,000 years of data, but we know that we will never ever have 2,000 years of data. So this optimal distribution is dependent on the total length of our data record. And we have repeated this for shorter, reduced data records. In this case, it's for 200 years of data. And we can see that the best performance here is using operators that are 50 years long. So mainly what we get with this is like, if we have a determined amount of data, there is an optimal distribution of using it for getting like the maximum skill. So let's go to the recap and some open questions. What we have seen is that we can use Koopman theory to get successful answer forecasts. And also we do know now that there are robustness issues that can be tackled using our Koopman ensemble forecasting approach. And also that this approach is able to capture nonlinear predictability and to outperform the current state-of-the-art lim data-driven methods. We also have had a look on some other things, for example, the spatial distribution of the ACC, and we have gotten some interesting results. And also we have had a look also in the reliability of the forecasts and also the extreme events forecasting. Someone asked before about El Niño and La Niña symmetries. We are not completely done with this study yet, but we have had a look on that too, in the different reliability of El Niño and La Niña. And yeah, actually, as Antonio said, this method is able to, mathematically it gives the space for non-symmetries to arise. Then the point is if they do or they do not. But there are a lot of open questions, like what happens if we start applying this to observational data, in which we have non-stationary dynamics and also much more noise. And also, are there better ways to reduce the noise in the Koopman operator spectrum? And overall, like, what is the best forecasting framework that we can use if we want to get better forecasts? So mainly this is all. I will be very interested to know if any of you have suggestions for these open questions. Some of you already talked to me, but I will be very interested into that, so feel super free.